does not change a lot, but we look at the protein, it's reduced about 50 to 60%. So this reduction kind of indicating this long form RNA is actually subject to the translational control, and we believe it's CPV2. We just never really crossed these mice with CPV2 knockout again to demonstrate this, but that's what we think. So we think that this mice is just like a CPV2 knockout. Without the proper 3' UTR, they cannot be translational upregulate. And we calculate the RNA level versus protein level. We think a long form can be translated more efficient, probably 15-fold more efficient than the short form. Okay, so how about human? So with the human, we actually purchased this RNA from the biologics. And in the human, there's no short form, they only have a long form. And if you look at their transcript sequence, they only have one polyase signal, they don't have the other one polyase signal. And we do experiment actually confirm, yes, human only have a long form, not like a mouse have a long form and short form. And this is just out of curiosity, we actually do quantitative RT-qPCR. So in the mouse, the UCPR RNA is really, really high. And compared to the human, this is a log2 difference. So and this is like a 6, 2 times 6 is like a 30 to 300 difference. And also you can see in the mouse, each mouse their amount is more or less the same, but with this 5 human samples, quite variable. And the CP2 RNA in both are very similar. So we just think at that time we quickly take this amount of RNA. If you think that the long form is translated more efficient, we think they can make up the protein difference. Maybe human to mouse, the protein difference 1 to 2 or 20-fold difference. Then we just we have no human sample. All we can do is do the reporter assay, take the human 3' UTR, put it in the brown adipocyte, do the reporter assay, and suggest they can be translational regulated by CPV2. And our finding actually agree with this study when they actually can take the fat from human sample and they do the UCPR activity measuring. They say in human bat, their activity probably is 1/3 of the mice. So based on our calculation, we think it's quite close. This translational upregulation can make up the very reduced amount of RNA in the human. Okay. So finally, I think I want to, when I have this UCP1, right, what else we did? We did a neuron-specific knockout, we did a adipocyte knockout. This adipocyte is knockout both brown fat and also white fat. We confirmed this knockout in the fat tissue can see the body weight increase, and let's also see the reduction of the UCP1. And we actually, to be sure this is brown fat, not a white fat, we infect the brown fat with the AAV virus. And we also show this is a knockout. This is the magenta line here. And when you have a wild-type virus, you can reduce the body weight to this blue line here. Okay. So with all this, initially when we sent out the story, we want to say because we found there's a regulation of the UCP1 and there's a reduction of the UCP1, so the mouse get fat. We have so much difficulty. Why is that? Because for people who are working in the UCP1, they all know based on UCP1 knockout study, UCP1 knockout study does not become fat. So this is initially I thought it's a quite easy story. You just have reduced thermogenesis. You should have a body fat increase and you should gain weight. Why is the result is so different? So here, go back to some of the data I have. It's like when we do this metabolic chamber, both male and female, both the knockout, wild type, long form, deletion form, and knockout. The only thing we can find difference is only in the knockout, female, and also some UCP1 knockout. We also can see some difference. But this is considered the energy is potential in the metabolic chamber. But using this setup to really look at the thermogenesis, usually people put it in the 30 degree. Because 30 degree is a thermal-neutral temperature for mice. This is also something new to me, like a thermal-neutral temperature. Indicating if you put a mouse at a 30 degree, they're quite comfortable, which is hard for me to imagine, but that's the case. It's like you put it at degree. There's thermoneutral, their fat is not function. Then you can inject a chemical to induce the fat activity. Now we can monitor this metabolic change. They indicate thermogenesis. If we do this, we found both in male and female, the UCP1 long-form knockout and CPU2 knockout, they all have a reduced thermogenesis. And we did quite a lot. We also did so-called PAD assay in mice. We can inject the isotope label deoxyglucose into the mice, and we monitor their change. And we can see a reduction in the knockout, both male and female, in the fat. And after co-exposure to increase the fat activity, we also see a reduction in the knockout. But the truth comes to when you monitor their body weight. CB2 increase, UCP1 knockout female increase, but takes quite a long time. But now with the short, long-form knockout. So to this end, we also think just by reducing UCP1 amount is not sufficient to reduce body weight. Also through this study, we found if you do the conditional knockout, you bypass this respiratory stress during early postnatal, you also see the male body weight increase. And so if this is called the data, depends on how you look at it. This is initial the body weight curve we have from the male. If you minus the initial body weight, as I told you, usually they have a reduced body weight to start with. And you can see there's still the body weight gain is increasing in the male. So in conclusion, after this, just looking at the body weight, we think that in the male, they also have an impaired fat function, and it will lead to the body weight gain increase in the male. And when we do this CT scanning to look at fat or lean mass in the knockout, this is also the same. Both female and male has this increased fat mass. So finally, I have to say to find this is really to the end, kind of try to conclude what can cause the body weight increase. And we take the bet to do the transcriptome. And as I just told you, for us, we don't care about the transcript change because the target we want is the transcript does not change. But I really out of my idea, so I just did a transcriptome. I look at transcriptome data, and quite surprisingly, we see there's an upregulated expression of the muscle gene. And we can see the upregulation of the muscle gene because their expression level is so low in the fat. So anything different is easy to, over twofold. So it can be easily picked up by company service. They usually set the cutoff at the twofold. And so this upregulated gene, when you search on the gene ontology, they're all muscle-related gene. And what does that mean? Not because our fat become the muscle, but it's because brown fat and muscle are from the same lineage of the cells. They're all from this B5 positive progenitor. And through this differentiation, the PRDM, a transcription factor, PRDM16, play a very important role to drive the differentiation to the brown adipocyte. So I just told my student, I think at the time I'm a postdoc, why don't we just back up PRDM16? And quite luckily, PRDM16 does decrease in the knockout. And this is also just at the protein level, but not at the RNA level. And so I think together, maybe with the UCP1, PRDM16, they all account for this body weight difference. So this is just some detail to confirm we can bind and activate the translation. I'm probably just going to skip this. But finally, what we did is we just do the rescue. If the PRDM16 is that important, can we inject the PRDM16 into the fat and also rescue the body fat? And in this case, we actually did the male mice. And we also see when we overexpression, we can see the PRDM16 can actually reduce the body weight on the knockout male. And this is correlated with the gene expression. Not only we can downregulate this so-called muscle gene in the knockout mice, but also we can, this is both wild-type mouse, when you're overexpressing the PRDM16, you also downregulate all the inflammatory gene expression. So together, I think we think that finally I want to conclude. I don't know whether this is the entire story, because I still think that the female can get super fat as something else, but at this moment I cannot tell you. So we think a CB2 activate UCP1 long form and PRDM16 translation is crucial for enhance the metabolic activity of fat and prevent the obesity. So I think this is the second part of our study. It's really kind of not intended to do, but finally lead to our really diverse study to the brown fat. So that's all the story I have, and thanks for your listening.
Okay, thanks to Huang for this outstanding